So what is density estimation? This is create a probability density function from a set of samples. So the pattern recognition lecture introduced parametric density function. So here they introduce ML estimator and MAP estimator. So we will break down these two estimator. So let's go into this part. So easy to understand, we use the analogy. So here we use the example of soup. So this is density estimation. We can analyze as making a soup. So this is like trying to figure out the recipe of a soup by tasting it. Think about, we taste a very delicious soup and we want to figure out which ingredients are in the soup, and I want to get the recipe from the soup. So here we will figure out the recipe, which is model parameter, from the data, which is soup, the taste of soup. So the taste of soup is the data, like x from x1 to xn, and zeta is the recipe that we want to figure out. So let's continue. You have some samples, like a spoonful of the soup, and you are trying to figure out the original probability distribution. So this original probability distribution is the soup recipe. So parameter, this is the soup recipe. So actually it is impossible to find the real original probability, but we want to approximate our zeta to the original probability, right? So parametric density estimation, in this case, you are making some assumption about the recipe. So let's think about our recipe as kind of linear and quadratic, or we can use random forest, something like that. So the model architecture is, we can say, is model assumption and assumption about the recipe. So for example, you might assume the soup is made of common ingredient, like a Gaussian distribution is good example. Then you taste the soup, collect samples, and try to figure out the best estimate for the common ingredient. So in this case, ML estimator, maximum likelihood estimator, is finding the recipe that would be most likely to produce the taste you are experiencing. So here, symbol zeta stands for the recipe you are trying to figure out. So zeta is recipe I want to figure out, and so this probability of from x1 to xn given zeta represent how likely the taste would be fit the recipe zeta was used. So we use parametric density estimation. We assume the parameter, which is the recipe, and estimate the taste. I mean, we estimate the zeta, the recipe, but we want to maximize the probability of taste given our assumption, which is recipe. So here we want to maximize this probability of taste given our assumption, given our parametric assumption, right? So if the parameter is Gaussian distribution, we have mean and standard deviation. If it is quadratic, we have the coefficient of each term, so like this. So now we understand this maximum likelihood estimator. This is just, we assume the model zeta, the recipe zeta, and we want to maximize the soup, taste of soup given zeta recipe. But what is MAP, maximum a posterior estimator? So posterior means posterior. So we want to maximize the posterior given prior knowledge. So here, this is similar to ML, maximum likelihood, but you are also considering your prior knowledge about the recipe. For instance, if you know the chef likes to use a lot of pepper, you might be biased toward recipes with more peppers. In this case, P of zeta given x1, xn represent how likely each recipe is given the taste you've experienced, and P of zeta represent how likely each recipe is based on your prior knowledge. So actually it is the position is changed at here. So why the position of condition was changed at MAP? So we will talk about this one. So in MLE, we want to find the parameter, in this case represented by zeta, that makes our observed data most likely. That's why conditional probability read as the probability of data given the parameters. On the other hand, MAP estimation includes an element of prior knowledge or belief about the parameters might be. In MAP, we are interested in the probability of the parameters given the data. So given the data, we want to estimate the recipe, which is parameter. So we want to maximize just this probability. This flips the condition around. We are no longer finding parameters that makes the data most like, but rather finding the most probable parameters given the data and our prior knowledge about the parameters. So first at MLE, we find parameters that makes the data most likely, but here find the most probable parameters given the data. So just the order is quite different, but basically after applying Bayes' rule, it is the same. Just they introduce the prior knowledge at here about, like, for example, the recipe use a lot of pepper. So in other words, MLE asked, given this parameter, how likely is the data? Whereas MAP asked, given the data and what I already know about the parameters, what are the most likely parameters? So the difference might seem suitable. So, but it's quite important. So it's just like so the reason applying Bayes' rule is just incorporating the prior knowledge. So the difference is incorporate prior knowledge from maximum likelihood estimator. So we use maximum a posterior estimator in the case that we know the prior knowledge about our assumption, our model, our recipe. Do you understand? So finally, let's talk about this parametric density estimator and non-parametric density estimator. So if you are using a parametric estimator, it means you are restricting yourself to certain type of recipe, like Gaussian. A non-parametric estimator, on the other hand, doesn't make strong assumptions about the form of the recipe. It could be anything. This can be more flexible, but might also require more data, more taste of the soup to figure out the recipe correctly. So okay. So let's recap about the maximum likelihood estimator, maximum posterior estimator. So it's just basically finding the parameter zeta which maximize this probability. So we use analogy, that is zeta is our recipe for the soup, and this x1 from x1 to xn is the taste of soup. So here we know the recipe is using a lot of pepper, so we have prior knowledge about the recipe includes a lot of pepper, so we want to maximize this probability, which includes the prior knowledge. So that's it. So I hope you can understand this concept, ML estimator and MAP estimator. So enjoy this video. If it is helpful for your understanding, please subscribe my channel and give like to me and have fun this journey of machine learning. So see you next time.